देखो दीवाने हुए जा रहे हैं, क्यों भी छोड़े छोड़े। Good evening, everyone. We're about to start. Okay. So, is it audible? Hello? Hello? Is it audible? Are you there, someone?
Yes, you are audible.
Okay. Um, so, so this is about week 7. Okay, we're going to do the questions of week 7. And so, in this week, in the previous week, we covered TD0, TD0 control, and Q learning, SARSA. Okay, these algorithms. Okay, so so the major focus today is on eligibility traces. Okay, so the previously that algorithms we have learned TD0, TD0 control, Q learning, SARSA. We will find the from 0 to lambda form. Okay, so today it will be TD lambda, TD lambda control, uh, Q learning lambda. Okay, like that. So what does it mean actually lambda? So we define the eligibility traces today, and that is what helps us to understand the lambda, the parameter here. Okay, so that is what we are going to do, and so let me explain how it is done. So to get this question done, uh, okay, so let's get started. So previously TD0 was done. From TD0 today it becomes TD lambda. So what is this parameter lambda? Okay, that is what we have to understand, and how to uh, write these new algorithms TD lambda, TD lambda control. Okay, So here, so you define the reward return, okay, Monte Carlo, this is what it denotes, okay. So this is equals to RT plus 1. uh, so where are you guys currently, means like uh, which which uh, week are you currently studying? NK, if you can tell me that. Which week you're currently in? Okay, okay, so let's continue. So so this is our uh, return, okay, and this is our new that discount, okay, RT plus 2, okay, then new square RT plus 3, so it goes up to uh, new to the power t minus small t minus 1, okay. So as you can see, so the power, as you can see, it is like first new to the power 0, new to the power 1, new to the power 2, and this is the 1, okay. So what does it mean is that uh, the number of terms here are t minus capital T minus small t. So these are the number of terms here, okay, and the final reward is RT at capital time T, okay. So what it actually means, okay. So at current time small t, okay, the return at that point depends on reward that you received up to the end, okay, and so the end happens at time t equals to capital T, and the number of such actions taken are capital T minus small t, the total number of steps taken, okay, or action taken, and so that is what is written at t plus 1. This is the reward is RT plus 1, RT plus 2, like that to R capital T, okay. Okay, so next thing what we do here is so we see that this, like TD here for TD method, R T plus 1 plus new times V ST plus 1. So how does it become? So previously we have seen that this VST plus 1 is the value function, right? And so how do we define the value function? So value function is the expected return of wait a minute. So value function, as you can see, we have defined in the Bellman when we were deriving the Bellman equation. The value function V pi s is defined as expectation over pi gt slash st equals to s. For state s that you are at, the expected return is the value function, okay. So what we do, this is new, okay, this is new for you and this is for st plus 1 state, okay, this is where it comes. the expected reward is given by the value function. So we given replace it by the value function. Okay. So approximately it is that. Okay, the expectation is over policy till the end. Okay, but even up to capital T, which is a lot of steps, till we get close to the finish of the actions that were required to be taken by the policy. We can approximately say it is like the value function at state st plus 1. Okay, any doubt up to this point? Okay, and we write this as gt1. Okay, so it is called one step truncated return. Okay, so this is the one step we have taken, and then you have truncated, then the approximation. Okay, so that is what we have done here. Similarly, the two step truncated return, so it is written as gt2. It can be written as rt plus 1 plus rt plus 2 plus nu square v st plus 2. Okay, so this is our two step truncated return. Okay, similarly it can be gtn. So after n step you truncate it. Okay, so that is what we have asked here, the corrected n step truncated return. So you have to write that one. So you have to just extrapolate to n. Okay, so how are we going to do it? So gt2 is written. Okay, so rt plus 1 to rt plus 2. So for n it will go to rt plus, from starting from rt plus 1 to rt plus n. Okay, first need to look at that. Okay, so this is not correct, of course. Okay, because it will start from rt plus 1. Okay, then finish at rt plus n, which is this one seems correct. Then gamma should not be there at first, so that is wrong. So answer is this one. Okay, so it start at rt plus 1, then this averaging with gamma, then this gamma to the power n vt st plus n. So this is the correct answer. Okay, so this is how we do the first question. Just from the theory it is very easy to do it. Okay, any doubt here? Any doubt? NK?
No, 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 no. Okay.
So let's continue. So we have not defined the eligibility traces till this point, which will be required for this question. Okay, so extending from our derivation here. Okay, we proceed further to get to our equation that will be able to, that will help us to solve the question. Okay, so here the first thing to understand is that in this week it is very important to understand the distinction between online and offline method. So in online method what you're doing is that uh, as soon as you get the reward return gt. Okay, so you update the value function. Okay, and then you continue after that, again calculate the gt, then update the value function, then again update the gt, calculate the, like that. Okay, so that is the online method. And in offline method what you do, the value function that you have, you update it till the end of the episode. Okay, means you keep it same till the end of the episode, and then update it, then again a new episode starts. So this is called the offline method. Okay, so that distinction is very important for us uh, as we proceed further in this week 7. So next what we have is the important point is the variance in estimation in an online method is higher. Okay, why? Because you are not taking every possibility into consideration, okay, leading to uncertainty. Okay, so the variance is higher. Okay, so moving on. So when we want to update this value function, so the delta v that we're going to add to vts is delta vts. Okay, so this is it. Okay, so this is what we're going to do. Vt plus 1 s to calculate vt1 vt plus 1 s, we have to do vts plus delta vts. This is what we have to do. So in an offline method, what happens until all the n steps are done, this change will be 0. But in online method, after every step, this will be updated with delta vts. Okay, so this is our point here. Okay, online and offline distinction. Delta vts is here defined as alpha times gt is the return, gtn so what is the point here, that you want to find this one. Okay, so for that you are adding something. So the point is that return at that point, at t point. Okay, and the value function at that point. Okay, so that denotes the error that we have. Okay, so when you're estimating the return, okay, so that's the accurate one. Value function is the approximation till time capital T. So alpha times, you can say this is a parameter regularizer or something, and then we are calculating the vt plus 1. Okay, so in case of offline method, you will keep adding this uh, v delta vt for t steps. Okay, for the whole process that you have, then you will update the delta vts. Okay, so this is our theory here. And so next what we're going to do is so next concept in this is the this from psychology. Okay, so what happens is that so this is the time that is moving forward. Okay, and at time capital T, the process end, you get the reward, and you want to distribute the reward to all the possible states where something means which deserves a reward. Okay, means the states at which something happened. Okay, something meaningful happened which led to the final solution. Okay, so you want to distribute that. Okay, so this art of like when you are this at point, so this you are at future and you're looking back here. Okay, so this is called the backward view. Okay, backward view of td lambda. So you're focusing at backward view of td lambda. Okay, so the concept is something like this. Okay, that so this is the like the heart and core of the eligibility traces point. Okay, so so as soon as something happens at one state, you give it a eligibility of 1, so it goes up 1, then it starts decaying. Okay, again something happens. Okay, you give an 1 again. So this different methodologies are there, so you can add this to the this 1 to the existing what is there, or you can just make it absolutely 1 and then decay it. Okay, so this is what happens. Okay, and so we keep on doing like this. Okay, so this is called the backward view. Okay, and uh, so the point is that uh, so also there is a forward view of TD lambda. So so here what you have is like, so you are at present state. Okay, and so these all have happened. Okay, and now you want to calculate what will be the return here. Okay, so this is your question. Okay, so the point is that this GT lambda we define as anything which is like with sum of 2, the coefficient sum of 2, uh, 1 here. Okay, so you're taking average of all the rewards return up to that point to calculate the future return at lambda. Okay, okay, so this is our point here. Okay, and what we got to do here is this GT lambda. So this is like for 2. Okay, so for multiple steps, that was like t minus small t steps for us. Okay, so these are the total number of uh, time steps that you have here. Okay, and so these number of actions were taken. So you write it like gt1 for first one. Okay, and lambda gt2 dot 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 lambda to the power t minus 1 gt. Okay, so this is how it happens. Okay, and now the thing is that these all should sum up to the coefficients should sum up to what? Okay, so for that we multiply the whole thing by 1 minus lambda. Okay, so how does it work? You take 1 minus lambda common here and sum of these. Let's see what we get. Lambda to the power t minus 1. Okay, so this is a GP. Okay, 1 minus this lambda to the power number of terms are t minus t, this t minus t divided by 1 minus lambda. This one cancels out, lambda not equals to 1. Now for multiple steps this high power can be ignored to 0, so you get this is equals to close to 1. Okay, Acha, for the whole process, so this goes to 1, but if you truncate it to capital T minus small t for a finite number of steps, what happens that it may not go to 1, okay? So you add this lambda capital T minus small t minus 1 gt, okay? You add this one. Okay, so this is a forward view for you, and next we again go back to the backward view and get to the eligibility traces. So what will be mathematically, it will be defined. So this is the eligibility traces at time t for state s. So this is defined as gamma times lambda. So gamma is the discount, lambda is this td lambda's parameter, okay? This is et minus 1 s, okay? So for the backward one, this is going on, okay? So if st not equals to s, okay, the state at which the the state at which the important action happens to get to the final state, desirable state at time capital T. Okay, so if you get to the the state at which something happens, so this becomes, so it was decaying, now it becomes this plus 1, okay? So you extend it up to 1. So this process is called the for st equals to s, it is called stresses accumulating traces, okay? Another is the replacing traces. So you don't add this one, you just make it one, okay? So this is another one, okay? So accumulating traces and replacing traces, this makes this one. So this is for now, okay? Now we can solve our problem, this one. Okay, so in a particular problem, the agent keeps going back to the same state in a loop. So this is our state, it keeps going back uh, in a loop to the same state. What is the maximum value that can be taken by the eligibility trace of such a state if you consider accumulating traces with lambda 0.5 and gamma is equals to 0.5? So what is happening is that so repeatedly goes to that state only, okay? This is in a loop, gamma lambda times this eligibility trace at t minus 1, okay, s plus 1, you keep adding 1, okay? Okay, that is the theory, right? So this state is the only state, so this is desirable state, so you keep adding 1 here, okay? So maximum value that can be taken by the eligibility trace, so maximum value what can happen here? So maximum value, how can you find out? Okay, so So first this say E0s starts with 0. Okay, so now you use this equation, so E1s, okay, becomes, or you can start this one as 1 only. So this becomes 1. 0 is 1. 1 is what? This gamma lambda plus 1. Okay, next what becomes? You have to use this multiplied by gamma lambda plus 1, like that it goes on, right? And so what do you get here is 1 plus gamma t is a t. So it's for 0, this was for 1, this for 2. Okay, so this one's for t. Summation over that from t equals to 1 to some t. So this is our expression for the tth es. Okay, now you want to maximize this one. Okay, so what happens is that we will take partial derivative here. Okay, gamma to the power t minus 1, first with respect to gamma, equated to 0, summation over t equals to 1 to say capital T here. Okay, confusion will not be there. Okay, next similarly for this is the expression you get here, and you can take this t out and cancel this one, so this one is not important. And now this is a GP, right? Okay, starting from lambda and then multiplying gamma lambda like that. Okay, so this can become 1 minus gamma lambda equals to 0. This is our condition for optimality, for maximum to happen. Okay, 1 minus gamma lambda equals to 0. So I have considered here So let us take a small break here, okay? I'll come back after 5 minutes, okay? Okay, so let's continue. Okay, so this is not the way to do it actually. Do it more formally, better. Erasing this is difficult, so insert a new slide. Okay, so so what I do now is this ETS is equals to gamma lambda times ET minus 1s plus 1, right? So this is our recurrence relation we have. We consider here that E0s is equals to a constant, say A, okay, A. So E1s, what it becomes? E1s becomes gamma lambda A plus 1, okay. E2s becomes gamma square lambda square A plus gamma lambda plus 1, okay. This is what becomes. Next, E3s, what does that become? So you put that there, so it becomes gamma square gamma cube lambda cube A okay. Similarly we can write E TS as so this becomes gamma T lambda T A, okay, plus, now what this will become, as you can see, this sums over up to the end, so this becomes summation T equals to from 0 first, okay, 0 will give 1 here, to so let's write it K here, not T. This is K here, okay, K equals to 0 to T minus 1, okay, and this is gamma lambda K, okay. So this is our expression that we will have to maximize, okay. Now you're given that what you're given here, lambda equals to 0.5 and gamma equals to 0.5, so let's put that one, okay. So insert another slide here. Now gamma lambda 1 by 2, okay, so this becomes 1 by 4 to the power T, and what else we have here, multiplied A plus K equals to 0 to T gamma K lambda K. This is 1 by 4, so let's write that. This is 1 by 4 to the power K, and this net is equals to ETS. So this one we can write as 3 by 4, okay, 3 by 4 into 1 minus, how many terms are there? T plus 1, right? 1 by 4 to the power t plus 1, okay, plus so to maximize it, you take the derivative and equate to 0 here, okay. So okay, so this becomes ln 1 by 4 1 by 4 to the power t. Next, what we have here, when we take derivative here, is negative times ln 1 by 4 and 1 by 4 to the power t, and in the bottom what we have, 3 by 4. 3 by 4 will come here, it will become 4 by 3. So equate this to 0, so this cancels out to 0 here, so not required. And 1 by 4 t, we take this one common, this is equals to 1 by 4, okay, is that correct? This will become 4. How is it possible? What are we getting here? This is 4 by 3 na? So this becomes minus 1 by 3. And this becomes 1 by okay. So now you can understand, if t goes to infinity, this becomes 0, right? This is what it becomes, right? Because this other part is constant, okay? So this is the one. So if t goes to infinity, this becomes equals to 0, okay? And so here, if you take t equals to infinity, so this is very high power, so this becomes 0. This becomes 4 by 3. That is what we are getting here. Now we have another problem. I think the question is wrong here. The answer will be 4 by 3 here. Okay, this question is wrong. Answer will be 4 by 3. I'm like 100% sure here. Okay. Any doubt? Any doubt?
No, no, no.
Okay. So when lambda equals to 1 and gamma is equals to 1, which of the following is true? Yeah. So so the very interesting part is that if lambda equals to 1, gamma equals to 1, so the important thing you can understand from this question that we have done, that the traces were decaying. Okay, so here the traces do not decay. Okay, so that's the important thing. C part is correct. Okay, the value of all the states are updated by the TD error in each episode. All the states are updated by the TD error in each episode. TD error. This is called TD error, no? So TD error is not the correct one actually. So TD error, what is TD error? So this is the TD error. So RT plus 1 plus gamma times V old ST plus 1 minus gamma V old ST. This is our thing. Okay, so when gamma is equals to 1, so this is what happens. Okay, gamma, just you can write it as, remove this gamma. Okay, now this is what you get here, and is it equals to the TD error, and our original update for this V in this case is alpha times GT n minus BTS. So it is not the same. Okay, not correct. Okay, cannot equate this to as same. Okay, so this method behaves like a Monte Carlo method for an undiscounted episodic task. So undiscounted part is correct, so no discount actually, and episodic task. Okay, so episode is also correct, but is it like a Monte Carlo method? That is what we have to understand. Monte Carlo method, what we are doing is that we do not do the dynamic programming way and sample the whole tree, but in Monte Carlo method we sample only few probable directions. Okay, and so that is what we are doing here. Okay, and because if you go here, uh, you are updating after every step. Okay, and so that is why it's correct. Okay, you're not doing it dynamic programming way. So these two are correct, 3 and C. In solving the control problem, suppose the first action that is taken is not an optimal action according to the current policy at the start of an episode. Is not an optimal action. Would an update be made corresponding to this action and subsequent reward received in a Watkins Q lambda algorithm? Okay. So So what they have written here is that, so we have a control problem. So first action is not optimal. So first let's go to what is q lambda algorithm here. So let's move methodically and it will be easier to solve it. Okay. Okay. So what we do is uh, to understand for first what I do is we understand the Sarsa lambda algorithm here. Okay. So it is similar to the previous Sarsa's algorithm, just some modifications are there. Gamma lambda so this is only if st is equals to s. Okay, so you get to the desired state and also take the desired action. Okay, for that. And next condition is that expectation for Sarsa will be equals to gamma lambda, it will decay. You don't choose the means otherwise. Okay, but what we also do here is that if you get to the state same state, okay, you get to the same state, you don't move to another state, you get to the same state, but do not take the desired action, then this so this is st is equals to s, you remain at that state, and at is not equals to a, then this becomes 0. Okay, so eligibility trace will become 0. 1 if st is equals to s and at is equals to a, so you remain at the state but you are taking the desired action. Okay, so this is what the Sarsa lambda algorithm is. Okay, so this is called the replacing traces. Okay, so this case you are replacing the traces, here you are making it 0. Okay. Okay. Now so in Watkins q lambda uh, what happens is so you are not taking optimal action according to the current policy. Would an update be made corresponding to the action subsequent so the point is that in Watkins method you do it greedy way, you always take the optimal one. Okay, you do not do it epsilon greedy, so I think that is the point here. Okay, so answer will be no here. Oh, no. So what happens here is that when you're starting to take an action, you're greedy, but your baseline is like all fuzzy in this situation. Okay, so that is why it is a yes. Okay, you're taking action which is not optimal, but you have to understand the baseline that you have, the policy that you learned is so bad that you are not able to take an optimal action. That is why it will be varied. The greedy part still remains. Okay, but this is the best you can do in this situation, so that is why it is yes. Okay, so it is a complicated question here. Given the following sequence of state observed from the beginning of an episode, what is the eligibility value E7 S1 of the state S1 at times step 7, given tk parameter lambda and discount rate gamma, initial value 0 when accumulated traces are used. Okay, so this is what we have here, and we are accumulating the traces here, and so these are the following sequence of states we have. So initially what you have E0 S1, that is 0 here. Next you move to E2 S2, and because S1 was 0, 1 2 3 4 5 6 7 8, E7 S1. Okay, so let's see the formula. Actually, I think that will help us out. So this is our formula here. So what we have is that T is here. We keep the same state here, and you're updating. Okay, so what we do here is that at t equals to 0, our state is S1. As you can see, we start with this. Okay, so no need to write again. Okay, next what we have is at t equals to 1. Okay, so E1, and this state become S2. How will you get 1 1 2 3 4 5 6 7 E7 is sorry, it makes sense. Yeah, we're getting that. Acha, so E1 S2 we get here. So it is going to be, so you get to the desirable state, right? S2 is the one desirable state here, and so it becomes gamma lambda times. Okay, any doubt? Yeah. So gamma lambda times, previously it was it was previously 0, so that will become 1 only. Okay, next what you have to do, E2 S1. Okay, so gamma lambda times 1 plus 1, this will become now E3 S3 will become gamma lambda times here gamma square lambda square plus gamma lambda plus 1. Okay, S1 again. Don't think we're doing it right. Am I doing wrong here? Okay, we take a small break here and then continue after that. Okay. Okay, so I'm back, and so you have to understand here that so S1 is our desirable state here. As soon as we reach there, okay, we get the +1 1, and otherwise it will decay. Okay, that is the plan here. Okay, so let's continue. Okay, so E0 is this. Okay, next what you have is you go to S2. So S2 is not our desirable state. So E1 S2, so this just decays. Okay, so you just put the 0 here and this becomes 0. Okay, next what you have is S1. Okay, so that is our desirable state, E2 S1. So this is 0. Okay, and so this will become 1. Okay, next what you have is E3 S3. Okay, not a desirable state, so it will just decay, so gamma lambda here. And next we have E4 S1. Okay, again our desirable state, so gamma square lambda square plus 1. Okay, so this is what we get here. This is E4 S1, so this is S1 here, we are currently at here. Now S3 you have to look at, so E5 S3, not desirable, right? So this becomes gamma cube lambda cube plus gamma lambda. Okay, now E6 S2, right? Okay, so this becomes not desirable, just decayed, gamma 4 lambda 4 gamma square lambda square. Now last one we have E7 S1. This is what we need, right? This becomes your desirable one, so decay plus 1. Okay, so gamma 5 lambda 5 plus gamma 3 lambda 3 plus 1. Oh god. To go to the sixth state as well, I think so. Yes. So this one we have reached. Okay, what is eligibility value? Uh, okay, but we'll receive the eligibility at the last. Okay, because it is an offline method, so you have to calculate that as well. So and final answer will be E8, actually S6, actually that is our answer. And you multiply it by gamma 6 gamma lambda again, undesirable one. Okay, so gamma 6 lambda 6 plus gamma 4 lambda 4 plus gamma lambda. So answer is this one. Question number 5 done. Question number 6. If replacing traces was used, so you replace it by directly by 1. Okay, if it comes equal to the state we desire. Okay, so let's do that again. Okay, uh, so we start with E0 S1 equals to 0. Next what we have is E1 S2. Okay, and this is equals to so this is equals to E1 S2, right? So E1 S2 is not desirable, so it would remain 0 here. Okay, and so in the desirable case directly becomes 1. Okay, replacement traces here. Okay, so let's see now. So in S1, this is a desirable one, so E2 S1, so this becomes directly equals to 1. Okay, E2 S1 done, and then E3 S3, undesirable one, so decayed. Okay, gamma lambda. Next what we have is S3 is done, right? This is S3 one, and S1 again, so S1 again, so it becomes again 1, S1 equal to 1. Next what we have is S3, so E5 S3, and this becomes equals to not desirable one, so decayed lambda gamma. Next what we have is S2 is there. Okay, so E6 S2, E6 S2, so undesirable one, so let's decay it. Okay, so lambda square gamma square. Okay, next what you have is S2 is done, right? Next what you have is S1, so desirable one, it becomes 1. So, okay, so E7 S1 equal to 1, and E8 S whatever that is S6, this becomes is equals to lambda gamma. Okay, so the answer is lambda gamma 6D. Okay, so this one is done. Next question is, the idea in SARSA lambda is to apply TD lambda prediction method to just the states rather than state action pair. So this one is wrong clearly. State action pair is what we have defined, I have written as well previously. Next question is this one. Eligibility traces provide a way to implement Monte Carlo algorithms in incremental fashion. Yes, that is correct. The lambda return can be set to Monte Carlo return, and which can be implemented using eligibility traces. So this is correct. Explanation also correct, I think. So it's the following correct way to implement replacing traces. So if this is equal, we get it to 1. Acha, and otherwise this is the correct one, 9D. Very simple question now. Consider episodic task and lambda is equal to 0, 1. Is it true that the one step return always gets assigned? Is it true that one step return always assign the maximum weight in the lambda return? One step return. Acha, one step return is the first one, right? Inside the maximum weight. Let's see. In the lambda return. Maximum weight. Most probably not actually, because other it's not known actually, because you're summing over lambda here, so which one gets the maximum is not known. The answer is no. And few other questions here actually. So GT3 what will be here? So this will become this one. Okay, and let us check. No mistakes are here. This one is correct. Okay, and this part is another cube. Okay, and t plus 1 step forward, right? Acha. So this is the one. This is the correct one. Okay. So consider state is a sanctioned account policy A1 is taken. The possible reason behind setting A is equals to A1 and this one equals to 0 is R. Reward obtained by taking action A1 in H not be attributed actions other than A1. Yes, so this is the correct one. It is the time step between reaching S are large enough to decay that eligibility trace to 0. No, this one is not correct. So first one is only correct. Okay, here state true or false. The ID and SARS lambda receptor TD lambda prediction method just the states rather than state action pair. This one is wrong. This one done. Actually, question is repeated. Is the TD lambda algorithm lambda equals to 1 essentially Monte Carlo? It is. Solving the control problem, suppose that the first action is taken. Acha. So we have done this one. Okay. So these are the questions today, and we are done. Any doubt? No doubt, I guess. So let's finish up here.